Okay, so yesterday we did the delay part, and from the delay part, Shivansh had a doubt. Shivanshu, can you please unmute yourself and can explain your doubt?
Yes, sir. Sir, while analysis, I found that जब भी क्या कहते हैं राइज टू फॉल का जो डिले है,
Hmm.
जब भी आइदर का डिले निकाल रहा हूँ
Hmm.
और राइज टू फॉल का डिले निकाल रहा हूँ और फॉल टू राइज का, तो
Hmm.
राइज टू फॉल का जो डिले है वो ज्यादा कंट्रीब्यूट कर रहा है आइदर के डिले में, इंस्टेड ऑफ फॉल, सॉरी, फॉल टू राइज का जो डिले है वो ज्यादा कंट्रीब्यूट कर रहा है इन
Hmm.
आइदर डिले रेदर देन राइज टू फॉल का डिले। सो सर
Ex-
वही डाउट था कि इतना ज्यादा डिले फॉल टू राइज में क्यों आ रहा है।
हाँ, दैट आई विल एक्सप्लेन। फॉल टू राइज का डिले आपका कभी भी किसी भी डिजिटल सर्किट में आप बनाओगे तो फॉल टू राइज का डिले हमेशा राइज टू फॉल से ज्यादा होता है। रीजन, let me explain that in English because there are few people who also wish to understand that in English. Why the delay of rise to fall is lower than from fall to rise? Why there is a difference? Because it always takes more effort to charge a capacitor than to discharge it. Let me explain you. Uh, where is my pen? There it is. MOSFET act as a capacitor, and in a capacitor, when you charge, it charges like this. And when you discharge, it discharges like this way. Discharging speed is always higher than the charging speed. In any of the circuit, be it a memory, be it your flip-flops or counters, any circuit that you will create, you will find that the charging part is always difficult than the discharging. Second thing, in the charging part, you have to control the MOSFET NMOS, and that is more difficult part. When we'll do the memory, I'll show that to you. But for now, please understand that when you will charge a capacitor, it will take more energy than to discharge it. Please see the characteristics of a capacitor, that will explain you everything. Right? MOSFET acts as a capacitor when you do this charging and discharging process. Tomorrow I'll take your class on delay on for the theory part, and if we'll be able to do the power part today, then I'll try to take your power, the class of power for the theory today only. Otherwise, we'll do that tomorrow. That is why I was saying that it is very important to understand that your power and delay, in both cases, it is very important to understand the theory part only. The simulation part will not suffice. Shivansh, this is a very good query, and this will happen every time. That is why I used to say that when you are working on a circuit, you need to check both delays. One is that when you go 0 to 1 and when you go 1 to 0. In digital electronics, when you create the circuits from MOSFETs, it is a very important part. And yes, one thing also, I think you asked in query. Let me read that. Where was that? Your doubt? Yes. Your query says that, sir, from the analysis, I find it peculiar that whenever the input is falling and output is rising, delay is higher than when input is rising, output is falling. Okay. Then the second query was, it is contributing more than we calculate either delay, right? See, एक चीज मुझे लगता है कि शायद मैंने कल थोड़ा सा एक गलत बोल दिया। मैं आई वॉज वॉचिंग दैट वीडियो। मैंने आपको बोला कि whenever you will use either instead of rising and falling, in that case it will show you the higher delay. No, it will show you the lower delay, right? In the first instance. And second, it will depend on that which edge you are taking, right? I'll show you today with example, then you all will understand. Remember, In any digital circuit, power part, calculating power is very easy, although understanding the power is difficult. In digital electronics, when you create it with this MOSFET part, this is in the physical design, the delay is difficult to find and difficult to understand. And more importantly, if you calculate the wrong delay, your whole analysis will go wrong. Why? Because when you calculate energy, there will be energy will be power cross delay. They usually they ask you to compute the power delay product. In most of the cases, you will see that when engineers design a product, they go for power delay product, PDP, in the research papers. Why do the engineers look for power delay product? Because why power? What is the power? Power is V cross I. Yani ki this is in your inverter circuit. This is VDD cross ID. Now you see that VDD that you give in the circuit is fixed. So this ID is changeable. This ID depends on two things. This ID depends on one thing is that it depends on the threshold voltage. Means that whether you are using SVT. Wait a second. I think. Okay. Whether you are using SVT, LVT, or HVT. Remember, in case LVT has the highest current, HVT has the lowest, and this SVT has the mid current. So the current depends on two things. One is the threshold voltage, and second is the width of MOSFET. Right? So there are two things when you calculate the current ID. We haven't started working on the width of the MOSFET. Probably in this week or next, we'll start working on this. As of now, we are understanding the basic working of power, delay, transistors, inverter, everything. So I'll come to the point. When you compute the power, see, remember, I'm talking about PDP, right? Till now, I said that power is V cross ID. In this VDD that you are giving is fixed. ID is changeable. And this ID depends on two factors. One factor is threshold voltage. Second factor is width of MOSFET. In any case, if you try to increase the current ID, let me say that you increase the VDD and you use the LVT transistor. In both cases, your ID will increase and ultimately your power will V cross, by virtue of V cross ID, it will go higher. But think about the MOSFET. Whenever you will increase the current, increase current means increasing the speed of electrons. And increasing the speed of electron means electron is going from source to destination in a very fast manner. It means the speed of your circuit is going upwards. Now, if the speed of the circuit is going upwards, the power is also going upwards because ID is increasing. See, we need high speed circuits, but we do not need high power consuming circuits. If you try to reduce the power, you cannot change the VDD. You can change the current only. And if you will reduce the current, your speed will also reduce. Right? You want power to go low and speed to go high. That is why whenever the engineers create the low power circuits, it is advisable to check for the power delay product, because everyone knows that reducing the power will increase the delay. In that case, suppose let us take an example. An example is that in a particular circuit, I have the power of 1 microwatt power consumed, power dissipated, let's say, and the delay is let's say 1 picosecond. You reduce the drain current and power reduces to 0.5 microwatt, but the delay increases to 5 picoseconds. Now, in that case, when you will compute the PDP here is 1 attojoule, right? 10 to the power 18 is attojoule. So, and here it will be 2.5 attojoules. So the PDP is lesser over here and it is very high over here. So this circuit is performing better, right? Now one has to see that you have reduced the power, but you have increased the delay. How do we use it? We actually create the circuit in digital electronics with different applications. For example, I need the low power circuits. Where I need the low power circuits? I need the low power circuits in hilly regions, the regions which are non-reachable. There you wish to maintain the device for long. You need the low power devices. You do not care about the performance. That is why in the recent time you might have seen that even your internet works slow in the hilly regions, because the devices, all the devices installed over there, they they work very slow, because they are supposed to reduce the they are supposed to work on the low power circuits, and working on low power circuits actually impact their performance. But in any case, if I want to work in any biomedical devices, I want to work on some medical emergency based devices. In that case, I want this device to act as fast as possible. I do not care about the power. So in that case, I make very high performance device and do not care about the power, knowing that the power consumption will also be very high. So in all the devices where I need the high power, high performance, the power consumption is supposed to be very high. It will be very high. And in few cases, when we create something which is a high performance and which is this high power also. So performance and power both are high, which means that your area will also be very high, right? Power dissipation low, but the performance is high. If you want both things to happen, in that case, the area will be high. So you have to make the trade-offs. Yesterday we have worked with the delay part. Today we'll start reading about the power, and we'll talk about different sort of powers in the circuit. Right, let's start. If you and any of you have any doubts regarding the power part, any specific things in the mind, you can please ask in the first go, so that I can keep on my discussion accordingly. Do you have any specific questions about the power consumption? It is a very interesting part. I'll start working with the same circuit of inverter, or what I'll do, I'll make a new inverter. I'm very happy to see that many of you have started working on Cadence and you are re-performing the experiment that I'm doing. That is very great. This will make you very easy on this tool. And once you start working on this tool, you'll start getting the experiences that how to connect with theory. Now I'll make the circuit quite rapidly today, because I'll not explain it today that how to make it. You all know. Okay, so I'll make it a simple manner. I'll not go with all these pins. I'll make it in a simple manner that the way you should do in. I'll go with analog library. Uh, Let us work on 0.8 volts. Right? Okay, so here you get the circuit of inverter. Now I'll launch ADL. We are working on 0.8 volt. We will do the transient simulation for 100 nanoseconds and outputs to be plotted. Select on design. There you have output. I need input also. So I'll rename this wire as in there. Now you see there is a functioning of inverter. I think nobody of you is having doubt until this point, right? We all are on the same page. Okay. Yes. So now I need to compute the power. To compute the power, we all do actually, I would say, use the word, we all do one ritual. What ritual is this? I'll go to the output, go to save all, and there you see different. Select signal to the output, all signals. Select power signals to the output, all signals. Select device currents, all. Select AC terminal currents, yes, this all. You can leave this yes or no because we are not using AC. So we can use till here. There you have PSFXL. This will also be required after some time. Okay. Now we need to, before we need to calculate power, once we do save all, we'll run the circuit again. Now we'll go to tools, result browser, and there you see this window, this output window. Here you see the word tran, this tran. Double click on this, you will see column PWR, power, right? Right click on it, go to calculator. You get this formula of power here, right? Then you go to the function, then all functions. There you have all the functions. Click on the average, right? Now you want this formula on your ADL. Press this button. Send buffer expression to ADL output. Then you will see this in your ADL, this formula in your ADL. Once you double click on it, you have this setting output option. Right here, power. Now you can see the power over here. When you will again simulate it, you see it is showing power 2.4167 pico. I'll write it down somewhere. The power consumption is 2.4167 pico, and your input is 1. In what is the meaning of input 1? Let us understand from the circuit. When you give high voltage from here, high voltage to the circuit means that your NMOS is on and high to PMOS makes PMOS off, right? It means you are getting this as a open circuit. No voltage is coming downwards, and it's about only the leakage current of PMOS. This is 2.4167 pico. We can confirm it from one more way. There you have seen this tran option. You see there is NMOS power. Take the average. Calculate. This is 149.2 10 to the power minus 21. So it is almost negligible NMOS power consumption. Then you see the power consumption of PMOS. This PMOS power. Take the average. You see 2.417. Almost whole of the power is being consumed by PMOS. If any of you is having doubt in this, what I've told, please let me know. I'll explain again. I just proved you that whole power is consumed by PMOS. But remember, only NMOS is on. The MOSFET which is on is not consuming the power. The power is being consumed by the MOSFET which is off. Should I explain this?
Yes, sir.
Okay. See, when you give high from in inverter, when you give high from input, it makes this transistor on and this transistor off. Remember, when this transistor is off, it means it is not allowing anything, right? And here you do not have anything on the output. Output is 0. So what it is discharging? Nothing. So work done by NMOS is close to 0, although it is on. But this PMOS is resisting this VDD to come over here. So the whole work is being done by PMOS. the power consumption is all about the work done, right? I repeat this whole process again. See this. The power consumption is all about the work done. When you give high from here, NMOS is on, PMOS is off. Here you do not have anything on the output. Is NMOS is on, so it is making it short circuit. But what this short circuit is doing, virtually this short circuit should drain everything. But what is draining? Almost nothing. It has nothing to do. It is like you have gone to office, but you are not doing anything. But here it is the PMOS, which has a VDD here, 800 millivolts. It is trying to come over here downwards, but since this is off, it is not allowing anything to go downwards. So whole work is being done by the PMOS only. So that is why the power consumption is being done by PMOS. That is evident from the fact that when we check the output from this ADL, what we have seen that I'll show you the process again. I have simulated the whole power consumption is 2.417 picowatt. Now, if I check this, the power consumed by PMOS, this is PMOS power consumed. I'll take the average. You see, the power consumed, total power consumed is 2.417. Power consumed by PMOS is also 2.417. Means whole power is being consumed by PMOS only. The PMOS is the one which is dissipating the power because it is the only transistor which is doing the work. Now, you please tell me that if I change the input, which transistor will consume the power? Like I give 0 volt over here. Now, which transistor will consume the power?
NMOS, sir.
NMOS. Yes. Why NMOS?
Because in this case, the NMOS is in off state, or we can say open circuit.
Yes. When you run the circuit, let us check it from the output. You see there the power consumption is slightly higher. This is 2.730. Right? And let us check the power consumed by NMOS. .73. The whole power is consumed by 73. There are two things. One that I'll explain why NMOS is consuming the whole power, but you please notice that NMOS consumes more power than PMOS. PMOS is consuming 2.417 when it was off. NMOS is consuming 2.73 when it is off. Remember, NMOS consumes more power than PMOS even if it is off. Right? So let us see the reason why it is consuming more power. You see, we have given 0 volt from here. 0 volt means NMOS is off on 0 volt and PMOS is on. It is now making short circuit here. When it is making short circuit, it means whole 800 millivolts come over here. This whole 800 millivolts can also go to ground. But who is stopping it to go to ground? NMOS is stopping because NMOS is off. So if NMOS is stopping, it means whole work is done by NMOS only. PMOS is doing nothing. It is just allowing everything to come down. when PMOS is doing nothing and NMOS is trying every effort to stop it to the ground. So it means NMOS is doing everything. That is why it is only the NMOS which is consuming the whole power. I hope you all might have got idea that which transistors consumes power, why power is being consumed, and how do we compute the power consumption in this Cadence. But it is not the only power consumption type. I'll show you two more types. This total process is showing only the leakage power. This is the leakage power consumed. First was the case was the leakage power consumed by PMOS. Then the leakage power consumed by NMOS. Remember, when a transistor is off, when a transistor is in off state, the power consumed by that particular transistor is known as leakage power. Ideally, when a transistor is off, it is supposed to consume zero power. But if it is consuming some power, it means that power is called the leakage power. I hope I made my point clear, right? So now we'll see that what are all other types of power that can be consumed. There are three types of power I will show you today. One is the leakage power. Second power is what you call short circuit power. The third is the switching power, right? We have seen the static power or the leakage power, whatever you call it. Now we'll talk about the other two types of power. This is also called static power. This is called leakage power. So we call it by the other names in a few books. You will see few more names. I'm not able to recall every name, but you will see that it is being called by other names also. So now we'll talk about the dynamic power. The time for the this Zoom meeting is also over. Let us connect on the same link again, and I'll start working on the other powers. I'm closing this meeting. Let us meet on the same link again.